in these 20 minutes to present some of the exciting and crazy research work that we are doing in this new paradigm that we say is a hybrid AI human air traffic management systems. So my research starts from a question first. And the question is, can you drive using back-view mirror? Of course, it's a very challenging task, isn't it? And that's what many of the ATM systems are doing. They depend on the models, which are inadequate representation of the reality. They are very good at predicting the past, but are poor at predicting the future. The same models were there back in 2008, 2010, and they failed to predict the financial crisis. They all relied on the historical statistical data and cannot, unfortunately, adopt to new circumstances, despite there were telltale signs and people knew that a financial crisis was coming. But models are models, right? People believe them. And they say, model says everything is fine, but the system crashed. So that's why ATM system comes into picture. It's a complex system, as you all know. It's a system that operates on the edge of chaos, transition between orderliness and disorderliness. There are causal mechanisms inside, and the human intentions, they remain hidden. So it's not that straightforward to master such a system. And to add to the challenge, more spice to the challenge, the historical data which have the rare events, they are very limited. Just imagine a loss of separation, right? Airprox doesn't happen very often, or runway excursion doesn't happen very often. They are rare events. So there's limited information about rare events. And if there's a relevant data available, then such data is extremely noisy and is difficult to identify. So this is a unique challenge that air traffic management brings to the machine learning community. Now, what we as machine learning and ATM scientists, we are proposing a hybrid AI human paradigm. We are proposing to investigate and develop new models, methods, and techniques and systems which enables and supports the symbiosis and augmentation of both human intelligence and machine capabilities for a safe and sustainable, robust air traffic management system. In this paradigm, there's a Venn diagram that I'm showing here on the slide. What we are doing is we are combining the expert judgment, which is hidden in the data, and combining it with the relevant real-time data using multi-fusion sensor techniques, and then being able to do predictions. This Venn diagram shows our approach where we use human psychophysiological data from the sensors like radar, ADS-B, and others, as well as air traffic controller, voice comm, and human actions data. This data is learned back by the machine learning algorithms and fused with the real-time data for making an effective prediction. Now, this particular paradigm, I would like to demonstrate through 4 case studies or 4 research areas that we have recently published some work in. And these are classical problems in air traffic management. For example, air traffic conflict resolution, airside predictions, which include pushback prediction, distance estimation, and identification of speed of the aircraft on the airside. Go-around prediction, a challenging problem for the tower controllers, and mixed mode runway operations. So these are the 4 challenges that we took last year in order to see how we can bring in hybrid AI human paradigm and use machine learning techniques and develop new machine learning techniques to solve them. So I'll just give a brief overview of these 4 areas because of the limited time. This all research is in public domain, recently published, so you can go through the research papers as well. And of course, we can discuss them today after the presentation as well. So the first research that I'm going to talk about is about air traffic conflict resolution. And the research challenge that we were facing is, can a machine learn to resolve air traffic conflicts from air traffic controllers alone. In order to solve this, what we did, we proposed a reinforcement learning-based approach, which is capable of resolving conflicts in presence of surrounding traffics and, of course, inherent uncertainties. They are always there in conflict resolution maneuver without any prior knowledge about the set of rules. And this knowledge is coming only from the air traffic controller maneuver tasks. So this conflict resolution task is formulated as a decision-making problem in a complex action space. This research also develops a large a learning environment, which you see on the extreme left-hand side. This is the learning environment. This is an interactive and intelligent conflict solver, which learns the resolution of air traffic controllers through an interactive interface. Now, some of the recent research by the famous human factor expert Hinston, he proposed that air traffic controller sees the conflict in very abstract geometrical terms. So we translated a conflict scenarios into simplistic geometric fractals and let the air traffic controllers interact with them. Then we used a scenario state representation, a reward function, and a reinforcement learning algorithm inspired from Q-learning and DDPG, the Deep Deterministic Policy Gradient Algorithm. This proposed algorithm has a two-stage decision-making process. It used to train an agent that can serve as an advisory tool for the air traffic controllers in resolving ATC conflicts, learning from the prior collected air traffic resolution data. On the extreme right-hand side, you can see there is a sort of a heat map. This is a heat map generated by the machine learning algorithm, where it sees that these are the go area and these are no-go area. And based on that, it generates the conflict resolution advisories. Here in this slide, I can show you the working model. Let's see how does it look like. So this scenario is presented to a controller, and the blue is the ownership and red is the intruder. And there's a conflict there. An air traffic controller resolves it like a rubber band movement, moving it. On the right-hand side, you can see there's a black line which shows over here the distance separation indicators. All must be above this black line. And of course, air traffic controller have the responsibility not to deviate the maneuver significantly, just in case the aircraft go far away. So basically, learning from these simple actions, we then expose this learning to the machine learning algorithm. And showing them unseen scenario, we can see in this example, we were able to have 5 conflict scenarios that were able to resolve by the machine. 1, it failed, but 5, it accepted. So we click 1 accepted and it show the scenario, it was thrown and it was able to resolve the conflict. Another one, for example, this one, it failed. For example, here there was a conflict and the 2 aircraft conflicted with each other. So this is a simple example where we have used the power of machine learning to learn from the demonstration of the controllers. And then using those demonstrations, we were able to resolve the conflicts. Then what happens? Then how about the real environment? So in the real environment, the biggest challenge is whether this kind of resolution will be accepted by the controllers or not, what we call as a conformal automation. So conformal automation allows for increased acceptability of the automation tool by the air traffic controller. And the key trick in achieving conformity of automation in performing an expert task like air traffic conflict resolution is to learn the preferences of air traffic controllers, i.e. the strategies, and then learning and recommending a similar strategies when a conflict comes. So in this particular framework, we are proposing a machine learning based framework to learn and predict air traffic conflict resolution strategy using an ensemble model of regressor and classifier chains, basically. So on the extreme left-hand side, you can see there's a high fidelity air traffic simulator, Escape Light. And this Escape Light is, we have developed a conflict generator module, generates complex scenarios, and we have generated over thousands of scenarios. And we got air traffic controllers, and we classify them as experienced controllers and not so experienced controllers. And based on that, you can see ATC A is the group that represents experienced controller. A T group is the air traffic controllers which are not so experienced. And there's a set of config resolutions for a given config that they come. And then based using this particular data, the maneuvered flight trajectory, we were able to learn the config resolution strategies from the controller. So in this one, as you can see over here, the config resolution strategy we have defined as a tuple of the identification which aircraft is going to be maneuvered, what will be the time of maneuver initiation, what will be the deviation towards left or towards right, and how much cross track deviation will be there, what will be the intermediate waypoints which this aircraft will be maneuvered to. And these strategies are then given to the controller and then shown that this is a possible config resolution trajectory, completely learned from air traffic controller's own action. And we were very happy to report that, as you can see in the results, the classification accuracy is well above 99, 98, and around 98% for different machine learning algorithms that we trained and used. So air traffic controller were consistently choosing the config resolution strategies that were suggested by the machine. And these strategies were learned by the machine from the controller itself. In order to contrast, we also use a classical config resolution algorithm, KB3D, and shown the config resolution advisory from KB3D also. And in that case, only 33% of the config resolution advisory suggested by the KB3D were accepted by the controller. And in this case, over 99% to 98% config resolution strategy was selected by the controller. So this is the conformal automation approach that we have adopted in this research. Next is a very interesting topic, which is airport-airside prediction. In this research, we are facing a research challenge, or a question is as follows. Can a machine learn to detect, track, and recognize aircraft and vehicles in the airside movement area and can perform human cognitive functions, such as identify where the location of the aircraft is, which taxiway segment, which gate, which runway this aircraft is? What is the speed of the aircraft? What is the distance between two aircraft? And can we do a prediction of the pushback time just from the video data? No other sensor, no other feeds. Only the video data is there. So what we done in this case, we have developed a computer vision framework using convolutional neural network for the airport airside surveillance. Now, there are so many inherent uncertainties in gate pushback, in taxiway routing. So this task is significantly challenging for the air traffic controllers. So what we want to propose is a novel computer vision framework for the airport airside surveillance using cameras to monitor ground movement for safety enhancement and operational efficiency. As you can see that this is a controller, and this is so many cameras with the large depth of field view. There are actually 6 cameras. I'm just showing here 5. So stitching the 5 video feeds and then feeding this studio feed into a machine learning, deep learning algorithm was a challenge in itself. For this particular algorithm, we have 2 algorithms. One is based on the maneuvering area, and another is for the apron area. Apron area is for the activity identification and for the predicting the pushback of the aircraft time. And another is the maneuvering area, which is for the speed estimation and distance estimation. So in this particular research, we feed the airport layout and the camera and the video feeds. And then we have algorithms to do camera calibration, object detection, and object tracking. This on the extreme right-hand side shows the backbone architecture of the algorithm, AVNet, that we have developed, recently published in TRC. So this framework adopts both CNN and camera calibration techniques. And this proposed framework we applied to the video camera feeds from Houston Airport for maneuver monitoring and Obihiro Airport, Japan for pushback prediction. So on the extreme left-hand side, you can see that the aircraft is coming and the machine learning algorithm is tracking the objects, labeling the objects, and identifying when a particular event was happening. So when the tow truck was attached, when the gate was attached, when the cargo fuel loader has completed. And on the lower end, you can see the prediction of the pushback prediction that was happening. So this framework estimates the pushback prediction with the average error of around 3 minutes from the time an aircraft arrived, with the error rate reducing until the aircraft actual pushback event. So using this particular computer vision framework, air traffic controller can have a very good identification of the pushback time of an aircraft just from the video feeds available. The other video that is on the other side, this shows the video feed from the Houston airport. Here, what we are showing is the object detection of the aircraft. As you can see, an aircraft is entering on the extreme right-hand side, and the algorithm is able to detect the speed as well as the distance between the aircraft. Oh, the video is a bit jittery, actually. Not because of this, but because of, yeah. So we can estimate the distance between the aircraft and the speed of the aircraft, the location of the aircraft with very high certainty in this case. So object detection model that we have used in here is compared with YOLO and Efficient. These are the two state-of-the-art machine learning algorithms, and our algorithm, which is AirNet, outperforms them significantly on the metrics of ROC and precision recall ratio. The next problem that we took was about having a machine learning algorithm for go-around prediction. And in this research, we face a challenge. Can we learn the preference of the pilot and the features which actually contribute to a go-around event? As we all know, air traffic controllers have to deal with continuously congested airspace, especially in the TMA. And it's a very timely cooperation between the pilots and the tower controllers is required for a smooth landing operation. So go around or missed approach procedures are there to discontinue unsafe landing. And however, especially in a digital tower kind of environment where controllers have very limited information available for the aircraft on the final approach, we came up with a new safety metric based on the machine learning techniques to assist air traffic controllers in detecting and predicting go-around event. So what in this research, what we do, so this is the concept diagram for this. So we have the surveillance data from the go-around event at 2 international airports. Then we have the meteorological and airspace data. And then we feed this information to the machine learning algorithm for doing a go-around prediction. For this research, we have set up an experimental environment, as can be seen on the top left-hand corner, with a pilot in the simulator. So we have flown over 600 approaches under varying wind and weather condition, as well as visibility condition. So professional pilots rated on 737 and A330 flew these approaches. And then basically we were able to manipulate the weather and were able to collect the data for the go-around probability prediction model. So the proposed system starts predicting when the aircraft is around 10 nautical miles from the runway. As the aircraft is moving towards the runway on its final approach path, this particular algorithm is able to give the air traffic controllers a progressive sequence of go-around probabilities. It updates the air traffic controller what is the likelihood an aircraft is going to do a go-around. So the experiments were conducted at 2 airports. One was a high, traffic airport, Philadelphia Airport. Another is a smaller airport with the smaller GA aircraft dominating. So we were able to demonstrate that this model is able to be used at multiple airports with very little retraining. No need for huge flight data sets. And for at least 70% of the flights, we got a go-around probability greater than 0.83. 50% we were able to get the right go-around around 0.93. So we got some very good results in this research. This paper is coming in TRC as well, accepted to appear recently. The last research that I'm just almost over the time, is about the multi-agent deep reinforcement learning for mixed departure, mixed mode runway sequencing. So the research question that we found very challenging in this, as you know, a mixed mode runway operation, both arrivals and departures are allowed to land and depart using the same runway. This is a very useful strategy because it can improve the runway throughput significantly. However, it's a safety critical operation, and not every air traffic controller is certified to do a mixed mode runway operation. So this is a challenging decision for an air traffic controller, how to identify the natural gaps that exist in a arrival stream. And if a natural gap exists, it can depart an aircraft without violating the arrival departure and departure separation. So in this research, we developed a multi-agent deep reinforcement learning algorithm using a DDPG, the deep deterministic policy gradient, to train two agents. One agent is a departure range, and another agent is an arrival agent. So over here, we have a departure and arrival manager, and then there is a separation manager that looks after the reward function, delayed decision, and making a decision to hold or release the flight. The departure agent actually learns the departure slotting decisions for departure, while the arrival agent determines the time delay or the spacing decision for the arrival stream. We have developed a data-driven simulation environment, which is plugged into the ASMGCS system for the Singapore Changi Airport, and do the continuous learning based on that. So on this side, you can see this is the aircraft waiting for the departure. On the runway holding point, there is an arrival aircraft which is landing, and there's a departure aircraft. So the machine has to make a decision whether to slot a departure or not. On the top, you can see a space-time diagram, which is learned by the machine learning agent. So aircraft are coming to arrive, land. This is the runway threshold, and then they are doing the runway exit. This particular interface, as you can see, the animation, the aircrafts are coming, and there is a green button here to release the flight. So AI agent is at the moment sees there's no arrival and is able to release the departure. But at the same time, if it sees the flight, as you can see in the so there are some flights actually which are coming to land. In the top panel, you can see some flights now popping. So these flights which are waiting at the departure, we are able to release them. Then you can see in the top, there are some flights are about to come. These are the flights which are arriving. And there's a countdown timer as well, which the machine learning algorithm advised to the controller when to release the flight or to hold the flight. So this machine learning algorithms learns this completely from the past historical data, able to see when to release a flight and to obey the separation standards for the arrivals and identify the natural gaps. On the top left-hand corner, you may be able to see the metrics, the runway capacity envelope, where the algorithm that we have proposed performs way better than the maximum throughput capacity envelope using the standard mathematical models. Also on the lower right-hand corner, we can see if we prioritize arrival or prioritize departure, the improvement as compared to the theoretical mathematical model. There's a significant improvement that we have demonstrated in this algorithm. So we used Pygame to develop this interface. And this interface is taking the data from the ASMGCS system and is able to decide when to release a flight and when not. An initial version of this model was presented recently in the ATM R&D seminar, and a detailed version is coming up in a IEEE ITS transaction paper. So in terms of summary, machine learning definitely offers a new way of thinking away from the rule-based automation. And especially we are focusing on human-driven conformal automation. So a human hybrid paradigm where humans are in sync with the machine learns from the human, and humans are able to trust the resolution advisory or the automation advisory given by the machine. And we believe that machine learning can assist air traffic controllers to handle complex traffic scenarios, can augment human cognition in complex decision-making, and also to maintain situation awareness in a dynamic environment. So that was quick talk about my research at ATMRI in NTU Singapore. I'm happy to take any questions. I think I ran over time already. Thank you.
Thank you very much, Samir. So I would like to go to the Q&A session.
Yeah, thank you for the talk. I just have a question about your second model of computer vision, which is this airside prediction. So you showed the video with the bounding boxes. So did you also do it with the image segmentation? And the second question is, how do you handle if there is a second object which goes behind a vehicle, and then so for some time the object is not visible in the camera, and then it comes out. So yeah, is it treated as a second object, or it's like the same object which is being tracked that it went behind the vehicle? And the third part, on a very bright sunny day, how do you separate the shadows from the object?
Okay, thank you. I think I've got clearly understood your two questions, the last two questions. So the demonstration that I'm showing you is for a clear, it's not of a clear day, it's for a rainy day actually. But the experiments that we have conducted are for varying wind, weather, IFR, VFR, day and night conditions, all of them. So the algorithm is able to do classification, detection, tracking, identification in all visibility conditions. So this is one of the strength of the model. Second question is that if a object goes behind another object, so we use a time delay mechanism for the algorithm, where it not only tracks the past movement of the vehicles that are there, but also try to predict their possible movement trajectories. This way, from the historical data, we are able to predict where the possible paths for this vehicle possible are. So if they go behind a particular aircraft, we are still able to predict what is the possible location of this once it goes behind a certain other object. This particular video that I'm showing you here is used for the detection, for the prediction of the aircraft pushback time. So when the event of, for example, when a gate is connected or disconnected, fuel truck is coming, loading the vehicle, loading the fuel in the aircraft, these timestamps are very important in identifying the aircraft pushback events. So this information is used even if the vehicle has gone behind. We can use a time delay prediction model, which uses the past movement tracking trajectories of the vehicles on the surface and can see where the object is. What was your first question? I was not very clear on that.
It was just about, do you use only the bounding boxes, or you also use this image segmentation?
Yeah, we use image segmentation, bounding boxes, both of them, and bring them into the architecture, as the architecture over here mentions that we have around 8 layers in this, and we use object detection followed by the tracking, use camera calibration for the convolutional neural net prediction.
Okay, next question.
Yeah, hello Samir, nice to see you again. I have one question. Well, it's not a question. I am curious about the turnaround model. And do the predictions condition the action of the humans? I mean, do the humans act in the same way, having and not having the information from the model? In particular, the pilot. So I don't know if the question is clear.
Let me come to that. Oh, this particular experiment, right?
Yeah, exactly. So you said that you are providing to the pilot the probability of turnaround.
No. The air traffic controller, the probability of turnaround.
Ah, okay.
See, air traffic controller, if they have a good idea that this particular aircraft has a high probability of doing a go-around, they are very well prepared. They can think about resequencing, also can advise the pilot of the instability of the flight, and can have a kind of safety mindset. See, so this research is coming from a survey that was done on the tower controllers, and they were asked which event is most safety significant for you, and all of them mentioned a go-around event. So we came up with this idea that why don't we provide air traffic controller with a machine learning tool that can give them the probability in real time of an aircraft at 7 to 10 nautical miles from the airport about its go-around probability.
Okay, it's clear. Thank you.
Thank you.
Thank you. Hello, Samir. So it is late for you. Huh? It's Daniel. Just a question about the run. Have you got some initiative at Singapore about runway contamination checking with the UAV?
Yes. So that research is also using machine learning, computer vision algorithm. But the problem for that they haven't solved is about wake vortex timings when an aircraft lands and aircraft take off. So still the regulators are not yet very approved of using UAV in an airport-airside environment because they will breach the virtual dimensions at an airport with a flying object. So this is a research project in the happening to use computer vision algorithm to identify the debris and unwanted object on the runway. But it's an interesting research, yes.
One more question. Okay, thank you very much, Samir.
Thank you for your time. Thank you all. Have fun. Bye-bye.
Bye.